We will talk about overall inspection of silica. The importance of silica comes from high rate of findability in the Earth's crust, easiness of extracting and processing, validity of its properties for being used in various applications. So silica in nature can be found in the forms of sandstone, silica sand, and quartzite. And its crystalline forms are counted as quartz, tridymite, and cristobalite. In the right-hand side, we see that silica can be found in various forms, such as beta quartz, tridymite, and cristobalite. And these are all in different temperatures. And the melting point of silica is also really high. Therefore, it can be used in operations where elevated temperatures are needed. Also, transparency and chemical inertness are the properties of silica as well. Therefore, these properties make silica important. So, nanosilica can be given as a recent development. Its advantages properties can be counted as large specific surface area, strong surface absorption, large surface energy, high chemical purity, and good dispersion. So if we give an example about the use of nanosilica, it would be concrete actually. So the advantages of nanosilica to be used on concrete are better durability and mechanical properties, alternative for cement, enhancement on filling effect, enhancement on particle size distribution, decreasing porosity, increasing pozzolanic reaction, improvement in cement setting process, better cohesiveness of fresh mixes, and decreasing bleeding and segregation. So the industry and applications of silica can be counted as silicon production, glass production, electronics industry, refractory materials, and building materials. So for the silicon production, deoxidizer in steel production, engine blocks, cylinder heads, machine tools, dynamo and transfer plates, lubricants, ingredients for cosmetics industry, insulation for water transitions can be given as examples. For glass production, domestic glass when mixed with lime and soda, thermal shock resistance glass when mixed with boron oxide and soda, and aerospace and application glasses from high-grade fused silica can be given as examples. For electronics industry, filler material for epoxy resins in circuit boards, semiconductors, and piezoelectric applications can be counted. For refractory materials, we have two options. Refractory material durable against acidic environments just by itself, silica, and starting with silica material combined with other materials for other refractory applications. So finally, for the building materials, sandstone as an aggregate, silica involved brick, cement, concrete, drywall, and asphalt, and silica fume as a pozzolan and filler material in concretes can be given as examples. So in the left-hand side, we see the properties of silica structures. So we see that compressive strength of silica is really high, and when it is compared with an aluminum, it's still higher. So we can use silica in compressive applications, but and we don't prefer to use silica in tensile applications. However, thermal properties of silica are the most outstanding ones. So we see that thermal conductivity of silica is really low. And if we want heat and insulation in an application, we can select silica structures. Also, the coefficient of thermal expansion is also really low. So if we want our products to be resistant against thermal shock, we can select silica products. And as we see in aluminum, coefficient of thermal expansion and thermal conductivity values are higher than silica products. And also in the electric constant row, we see that silica products offer relatively low values. So it can be used in electrical insulation applications. So in the figure above, we see silica glass with changing quartz qualities. We see that for a broadened range of wavelengths, the transmission rate of silica is really high. So for a specific improvement of silica from a selected Nature article, we will talk about a change in the manufacturing method of silica. Silica in nanoscale form is a demanding material for industries such as microelectronics, electromechanical systems, and microphonics. But side effects of current production methods are emission of hazardous chemicals, complex manufacturing facilities, and hard to achieve complex 3D shapes. 3D printed nanoscale silica products get into the scenario due to the ability of 3D printing to achieve complex structures with a simpler, less hazardous process. An approach to produce 3D printed silica with sub 200 nanometers resolution is the consideration of this paper. To reach these sub-wavelengths, 2pp enabled an additive manufacturing of well-dispersed polyethylene glycol functionalized colloidal silica nanocomposite ink is performed at first. Then after 3D printing, pyrolysis and sintering are applied to get pure silica. Sintering at 1100 Celsius yields a high-quality amorphous glass, while sintering at 1300 Celsius yields a polycrystalline crystalline. So in the figure above, we see that a UV and a visible transmission spectra of the two types of the final forms, an amorphous glass and crystalline, measured among thick films of them with a thickness of 2 micrometers. It's seen that both of them are transparent in a good manner, but an amorphous glass it takes leads and just a bit. And in the figure below, we see that final silica products are doped with various ions actually. So it's seen the structure displays strong photoluminescence among the desired wavelengths. Especially the photoluminescence behavior of ER+3 in 1.55 micrometers makes the structure suitable to be used for optical telecommunication applications. So it can be concluded that final 2pp printed structures display well optical properties, and 3D printing can be used as the manufacturing method of silica products in the future. Thank you for listening.